Hi, I am Dr. K. Shahul, Professor, EC Department, Sedu Institute of Technology. In this session, we are going to discuss mechanical rotational systems. First, I will give the introduction. The model of rotational mechanical system can be obtained by using three elements. One is moment of inertia, that is J of mass, dashport with rotational friction coefficient B, torsional spring with stiffness K. So, we are going to model mechanical rotation system using these three basic elements. We will see one by one. Before that, we will discuss about a list of symbols used in mechanical rotation system. This is actually a rotation system, so we need to consider angular displacement in radian, that is represented as theta. The rate of change of angular displacement is called angular velocity, that is radian per second. D square theta by dt square is angular acceleration radian per second square, and T is the applied torque Newton meter square, and J is represented as moment of inertia. The unit is kilogram per meter square per radian. B is rotational frictional coefficient Newton meter square per radian per second. K is stiffness of spring Newton meter square by radian. So, these are the list of symbols we are going to use in modeling mechanical rotational systems. First we will discuss about torque balance equation of idealized elements. First one is ideal rotational mass. So, this is actually ideal rotational mass, a mass element, and 2n force is applied, there is torque is applied. Because of the torque, the mass element will rotate, and the rotation is recorded as theta, and applied torque is T, and moment of inertia is J. Let T is applied torque and Tj is the opposing torque due to moment of inertia of the body, because for any force equivalent opposing force will be given by the elements. Hence, T is the applied force and Tj is opposing force due to moment of inertia of the body. So, the opposing force T suffix j is directly proportional to d square theta by dt square, and when we are equating Tj, will get T suffix j is equal to j into d square theta by dt square. By Newton's second law, the applied torque is equal to opposing torque Tj, which is equal to j into d square theta by dt square. So, this is related to rotational mass element. Next one is ideal rotational dashpot with one end fixed to reference. So, this is the setup. So, this is reference, and a dashpot is dashboard is here, and a torque is applied on one end. Because of the torque, one side will rotate, because of that second side will get rotated. So, angle is theta, and now we assume that T is the applied torque, and T suffix B is opposing torque due to friction, and when we are equating it, we get T suffix P, that is opposing torque, is directly proportional to rate of change of angular displacement theta, okay, d theta by dt. So, when you are equating, we get Tb is equal to B into d theta by dt, which is equal to the applied torque. So, if the same dashboard is connected in between two different elements, then what will happen is we need to consider two different angular displacement. One end we have to assume that the angular displacement is theta 1, and another end the angular displacement we have to consider theta 2. and because of the applied torque, both side will rotate. So the opposing torque due to friction Tb is directly proportional to d into theta 1 minus theta 2 divided by dt. So theta 1 is angular displacement in one end and theta 2 is angular displacement in another end divided by dt. So when you are equating, Tb is equal to b into d theta 1 minus theta 2 by t is equal to applied torque. Similarly, we are going to consider ideal spring with one end fixing to reference. Here this is the ideal spring, this is connected with the reference and the torque is applied in one end. So this is the applied torque and the angular displacement recorded as theta. Now T is the applied torque, T suffix k is opposing torque due to elasticity. So opposing torque is directly proportional to angular displacement and T suffix k is equal to k into theta which is equal to applied torque. At the same time, if the same spring is connected in between two different elements, what will happen is, and at the one end we are applying torque. So in the one end angular displacement is different and another end angular displacement is different. So we are considering one angular displacement at one end is theta 1 and the another end is theta 2. Now the opposing torque due to the spring T suffix k is directly proportional to the difference between displacement in angular displacement in one end minus and angular displacement in another end, which is equal to T suffix k is equal to k into theta 1 minus theta 2, which is equal to the applied torque. These are the basic information related to mechanical rotational systems. Now we need to know the basic thing related to Laplace transform. So Laplace transform of angular displacement is equal to theta of s. Laplace transform of d theta by dt is equal to s into theta of s, and Laplace transform of d square theta by dt square is equal to s square into theta of s. And here we have to consider that initial conditions are is equal to 0. With this basic information, we are going to solve a small problem. So I'll read the problem. Write differential equation governing the mechanical rotational system shown in figure. Obtain the transfer function of the system, that is we have to find out theta s divided by t of s. Just see this setup. A torque is applied in one end of mass element, moment of inertia J1, and then a spring is connected, and then again a mass element is there, and then it is connected with the dashpot. The dashpot is connected with the reference, and I have mentioned the parameters related to each and every elements and also the torque. So when we are seeing this setup, we have two nodes. One node is at J1 and another node is at J2, another mass element. So we have to consider J1 and J2 as nodes, that is moment of inertia, and let Laplace transform of t applied torque is t of s, and Laplace transform of theta is theta of s. Laplace transform of theta 1 is recorded as theta 1 of s. So that is theta 1 is nothing but angular displacement at mass element J1, that is moment of inertia J1, and theta is the angular displacement which is related to moment of inertia J2. First we will discuss about first mass element J1. So in J1 there are three forces are three torques are acting. One is applied torque, another one is opposing torque related to moment of inertia, another one is applied torque related to the spring. So, this is the first node. So, applied torque and displacement is regarded as theta 1, angular displacement theta 1, and opposing torque is related to J1 and T suffix K. So, T suffix J1 is equal to, this is related to moment of inertia, already we have discussed about this, J1 into d square theta 1 by dt square. T suffix k is equal to, which is related to spring, which is equal to, this spring is in between J1 and J2. So, we have to consider two different angular displacement. First, when you are considering first mass element, we have to subtract first to second. So, theta 1 minus theta. By Newton's second law, the torque acting on the mass element is equal to 0. Sum of torque acting on the mass element is equal to 0. So, applied torque is equal to sum of opposing torque. T is equal to T J1 plus Tk, which is equal to, we are going to substitute the equations for Tj1 and T suffix k. Tj1 is J1 d square theta by dt square plus k into theta 1 minus theta. Now, we have to take Laplace transform. When we are taking Laplace transform, we get T of s is equal to J1 into s square theta 1 of s plus k into theta 1 of s plus minus k into theta of s. So, here we can take theta 1 common, and we can rewrite this equation as T of s is equal to J1 s square plus k into theta 1 of s plus k into theta of s. This is the first equation. Second equation is related to moment of inertia second node. So, that is a free body diagram of mass element with moment of inertia J2. In that mass element, there are three different forces are acting, all are opposing forces, okay, opposing force, opposing torque, in fact, opposing torque, and angular displacement is theta. Now, this Tj2 is the opposing torque related to mass element. So, Tj2 is equal to J2 into d square theta by dt square. Then Tb is related to dashpot. So, Tb is equal to b into d theta by dt, and k spring, Tk is equal to, this is actually common to J1 and J2. So, opposing force, opposing torque due to spring is equal to k into theta minus theta 1. By Newton's second law, sum of forces acting on a node is equal to 0. Here only opposing force, one is T suffix k, T suffix plus T suffix p plus T suffix J2, which is equal to 0. Now, we have to substitute the equation related to all these one. T suffix k is equal to J2 into d square theta by d square, then Tb is equal to b into d theta by dt, and then k is k into theta minus theta 1 is equal to 0. Now, we have to take Laplace transform. When we are taking Laplace transform for this, we get J2, when we are taking Laplace transform for this, we get J2 s square theta of s plus b into s into theta of s, then k into theta of s minus k into theta 1 of s is equal to 0. Now, we are going to take theta of s common outside, and we get J2 s square plus b into s plus k theta of s minus k into theta 1 of s is equal to 0. So, I am going to move this one right hand side, I get j2 s square plus b into s plus k into theta of s minus is equal to k into theta 1 of s, and we are going to solve for theta 1 of s. When we are solving for theta 1 of s, we get this one divided by this k, there is j2 s square plus bs plus k divided by k into theta of s. So we have two different equations. So this is the first equation and this is the second equation. We are going to substitute theta 1 of s in the first equation. So we get j1 s square plus k into this theta 1 of s. Theta 1 of s is equal to j2 s square plus b into s plus k divided by k into theta of s minus k into theta of s is equal to t of s. So I am going to take theta of s outside. When you are taking theta of s, we get this. First we will solve. When you are taking this theta of s outside, we get this one, this term minus this term. So you will get, so theta of s is equal to j1 s square plus k into j2 s square plus bs plus k minus k square, because why this k square is we have to multiply this k and this k. We get k square divided by k is equal to t of s. Then we actually need theta of s by t of s. So when you are changing this when you are moving this function, we get theta of s is equal to k by, so I am just moving this right hand side, I will get k divided by j1 s square plus k into j2 s square plus bs plus k minus k square. So this is the transfer function of the given mechanical rotational system. Thank you.